ever wondered why a crane never lifts a load randomly, or why a tall building doesn't fall even during strong winds? These are not mere coincidences, but are governed by fundamental principles of physics and engineering. Understanding these principles is crucial for safety and efficiency in various applications, from construction to everyday objects. The answer lies in one powerful concept: the center of gravity. This concept is fundamental to understanding stability, balance, and the distribution of weight in any physical object or system. It's a cornerstone of mechanical engineering and physics, influencing design and operation across countless industries. Welcome back to SimpleGyan. This is Chapter 3 of Properties of Bodies. Today, we'll understand the center of gravity from zero to an advanced level using real-life examples, detailed diagrams, and practical problem-solving logic. We will break down complex ideas into easily digestible segments, ensuring a thorough understanding. This video is perfect for mechanical engineering, diploma, and ITI students, as well as those preparing for competitive exams like GATE, SSC-JE, and PSU exams. The concepts covered here are frequently tested and are essential for a strong foundation in engineering principles. We aim to provide you with the knowledge needed to excel in these areas. So what exactly is the center of gravity? It's defined as the imaginary point through which the entire weight of a body appears to act, regardless of its orientation in space. This point is crucial because it represents the average location of the weight of an object. In simpler terms, it's the balance point of a body. If you support a body precisely at this point, it will achieve a state of equilibrium and will not rotate or topple. This principle is evident in many everyday objects and engineering designs, ensuring stability and preventing unwanted movement. For example, a crane hook is always meticulously aligned with the center of gravity of the load it's lifting to ensure maximum stability and prevent dangerous swinging or tipping. This precise alignment is critical for safe and efficient lifting operations, highlighting the practical importance of COG. Now, let's clarify the crucial differences between the center of gravity, center of mass, and centroid. While these terms are often used interchangeably, especially in introductory contexts, they have distinct definitions and applications that are important for a deeper understanding. The center of gravity is the point of total weight, applicable to bodies with mass and subject to gravitational force. The center of mass, on the other hand, is the point of total mass, representing the average position of all the mass that constitutes the body, whether uniform or non-uniform in density. The centroid, in contrast, is purely a geometrical center, applying specifically to areas and shapes, irrespective of their mass or weight distribution. It's a mathematical concept used to describe the geometric mean position of a shape's area or volume. An important exam point to remember is that for bodies with uniform density and operating under constant gravitational acceleration, the center of gravity, center of mass, and centroid all coincide at the same point. This simplification is often used in many engineering calculations. Let's look at the center of gravity for some simple, common bodies. For a uniform rod, its center of gravity is located precisely at its midpoint, assuming the material is evenly distributed along its length. For a rectangle or square, the center of gravity is found at the intersection of its diagonals. Similarly, a circular disc and a solid sphere both have their center of gravity located exactly at their geometric center. These are fundamental shapes with easily identifiable COG. A solid cone's center of gravity is situated at a height of h/4 from its base, where h is the total height of the cone. For a solid cylinder, its center of gravity is located precisely at its mid-height, along its central axis. These specific locations are derived from geometric principles. These standard results for the center of gravity of simple geometric shapes are direct questions in many engineering and competitive exams, so you must commit them to memory. Knowing these will save you valuable time during problem solving and ensure accuracy. When a body is made of multiple, interconnected parts, we employ the principle of moments to accurately determine its overall center of gravity. This method allows us to analyze complex structures by breaking them down into simpler components. The formula for finding the center of gravity of composite bodies involves summing the product of each individual part's weight and its distance from a chosen reference axis, then dividing this sum by the total weight of all the parts combined. This is represented by the equations for x bar and y bar. The systematic steps to apply this method are: first, divide the complex body into simple, recognizable shapes. Second, find the center of gravity of each individual part. Third, multiply each part's weight by its respective distance from the reference axis. Fourth, sum these moments. And finally, divide by the total weight of the entire composite body. This methodical approach ensures accuracy. For irregular lamina or flat, thin objects with non-uniform shapes, you can experimentally determine the center of gravity. This involves suspending the object from one point, allowing it to hang freely, and then drawing a vertical line downwards from the suspension point. Subsequently, you suspend it from another different point and draw a second vertical line. The precise intersection of these two vertical lines gives you the exact center of gravity of the irregular lamina. This practical method is widely used in various industries, such as in the design and fabrication of sheet metal components and for accurate crane load estimation in construction and logistics, ensuring safety and balance. Stability is intrinsically linked to the position of the center of gravity. A body is considered stable if the vertical line drawn through its center of gravity falls entirely within its base area. If this line falls outside the base, the body will become unstable and topple. A fundamental principle of stability is that lowering the center of gravity significantly increases a body's stability. This is why high-performance cars are designed with a very low height, and heavy industrial machines are securely floor-mounted, often with wide bases, to prevent them from tipping over during operation. In large-scale operations, cranes extend their outriggers to substantially enlarge their effective base area. This critical action ensures that the center of gravity of the crane and its heavy load remains well within this expanded base, providing maximum stability and preventing catastrophic accidents during heavy lifts. It's a vital safety measure. As a mechanical engineer, you'll encounter and deal with the principles of the center of gravity every single day, even if you don't always consciously notice its influence. It's an underlying factor in almost every design and operational decision, from small components to massive structures. The center of gravity is crucial in a vast array of engineering applications, including safe crane and lifting operations, precise conveyor and belt alignment, robust machine foundation design, stable vehicle design, and ensuring overall structural stability, particularly in the engineering of earthquake-resistant buildings. Its understanding is paramount for safety and performance. Common exam traps often include confusing the centroid with the center of gravity, forgetting to apply proper sign conventions in calculations, using the wrong reference axis for moments, or neglecting to account for removed portions, such as holes or cutouts, in composite bodies. These errors can lead to incorrect results. To effectively avoid these common mistakes and ensure accuracy in your calculations, always begin by sketching a clear and detailed diagram of the body or system you are analyzing. This visual representation helps in correctly identifying parts, reference axis, and the COG of individual components. To quickly revise the key takeaways, the center of gravity is essentially the balance point of an object. It always acts vertically downward. Its position depends critically on the distribution of mass within the body, and a lower center of gravity invariably means higher stability for the object. These are fundamental principles. Remember to use the moment method for accurately determining the center of gravity of composite bodies. If you found this chapter on the center of gravity useful and informative, please take a moment to like the video and subscribe to SimpleGyan for more valuable engineering content. Your support helps us create more educational resources. Comment below with COG done to let us know you've mastered this topic, and tell us which numerical problems or advanced concepts you'd like us to cover next. Your feedback guides our future content. Keep learning, keep exploring, and keep engineering.